Good morning, everyone. So today, for the last seminar for the whole academic year, we have Professor Caulfield. He is now, he's a professor in Cambridge. He's the head of the Applied Mathematics and Theoretical Physics Department. And
I was the head. I am not the head anymore. Very. Yes.
Stuff. So yeah, today we're going to learn a lot about turbulence, and thank you for coming.
Yeah, thank you very much for inviting me. Oh, thank you. And it's really nice to be back here again. Today I'd like to talk to you about the work of these two fine people here. The one on the right is Miles Couchman, who was a postdoc with me and Rich Kurzweil in Cambridge. Poor guy arrived during the COVID lockdown, so he was working with us as a postdoc, and we didn't meet him for 9 months, which was in person, which was very difficult for him. But he ended up things working out very well. He's now a professor, assistant professor in York University in Toronto. And the person on the right is Nico Petropoulos, on the other side. I'm chirally challenged. Nico Petropoulos, who was a PhD student of mine and has just finished a postdoc at CTR. And so I'll be hopefully trying to explain some of the aspects of these particular pictures, but I also will really want to convince as many of you as possible about how important the problem of stratified turbulence is. So here is a quite old video now that I find very inspirational. It was created by Kathleen Doan at Earth and Space Research up in this neck of the woods. And it is an amazing data set. It is ocean surface currents reconstructed from altimetry in real time. And so by quite precise measurements, satellite measurements of the surface elevation of the ocean, combined with the Navier-Stokes equations, assimilating it to put in the pressure balances and the fact that the Earth is rotation and so on, you can actually see these ocean currents. And there's several things that I want to highlight to you about these ocean currents. The first, you can clearly see that the Earth is rotating because something's happening along the equator. The color map is the speed of the flow. But the other thing that I really want to draw your attention to are the boundary currents that are typically transporting water poleward and also heat poleward on the western side of the ocean basin. So you can see I don't know if the pointer can be, we're just about visible. So you can see the Gulf Stream here, the famous Gulf Stream, transporting hot water poleward up from the Gulf, whether it's called the Gulf of Mexico or the Gulf of America, it's still the Gulf. And this is the Gulf Stream, and it's transporting heat here. There's also the Kuroshio, the one that goes along the east coast of Japan, and this one, the Agulhas current, going down the east coast of Africa, where you see this retroflexion, the fact that it is turned round by the fact that there is an enormously fast and high volume current going around Antarctica, the Antarctica circumpolar current, which is typically transporting something of the order of 100 million cubic meters a second of water around in this particular direction. And so why am I highlighting these particular currents? Well, because on average, they are near the surface transporting water poleward. And if they're transporting water poleward, they're transporting heat poleward. And it's really important to understand how heat is transported in the global oceans because of this particular data that's here. This is an amazing kind of review article. This is data. This isn't stuff from climate models. And though we are concerned about the fact that the atmosphere is heating up, whether we're going to go through 1.5 degrees centigrade or 2 degrees centigrade if we don't change our ways, fundamentally, since we've started industrial activity, something of the order of 10 to the 23, 400 or so zettajoules of heat has been gained by the global climate system. Of that, only about 2% is still in the atmosphere. The vast majority of it is in the ocean. You see this? 90% of it has got into the ocean. And indeed, the thing that I'm particularly interested in is nearly 40% of it, i.e. roughly 20 times the amount that has got into the atmosphere, has got into the ocean, deep in the ocean, below 700 meters in the ocean. And so fundamentally, what is happening is that as our activity that we are heating up through the greenhouse effect and also perturbing the ecosystems, we're heating up the global climate system, but the vast majority of that heat is going into the oceans. And this is really a statement to do with heat capacity. Because if you think of the heat capacity of the volume of air all the way up to the edge of the atmosphere above this table, now internationally we define the atmosphere as being up to 100 kilometers. That's called the Von Karman line, which is roughly where you stop flying and you start orbiting. Interestingly, NASA says you've gone to space if you go up 50 miles, which is only 80 kilometers, but that's a different story for another day. Anyway, all that volume of air, and I want to heat it up by 1 degree, the amount of heat that I have to supply to heat that volume of air by 1 degree is the same as I would need to heat only the same cross-sectional area, but a depth of 3.4 meters in the ocean. Now, the ocean is roughly speaking 70% of the surface of the Earth. Average depth is really quite closely 4 kilometers. So that's really telling you that the heat capacity of the ocean is vastly larger, and the way that heat is transported in the oceans is really a key question to address, I think. Oh, impressive. Right, and so here is it's 30 years old data, but it's the rough idea that you can get of the heat transport in the oceans in petawatt, 10 to the 15 watts. Now, on average, you'll see that there is something of the order of 2 petawatts. You look at the solid line is the total. Something of the order of 2 petawatts is going poleward, right? And it's the same, roughly the same in the two hemispheres. There's an interesting detail which is not in the Atlantic. You'll see that the dash line there is always positive, is always going northwards. I can't really see the button anymore, but it's always going northward. So it actually, because of certain aspects of the global climate system, in the Atlantic, you have a northward transport of water, but that is overwhelmed globally by the Pacific and the Indian Ocean, showing that on average, you have poleward transport of heat of the order of 2 petawatts. And then you stop and think about that, and you say, okay, what does that actually mean for the circulation in the ocean? I have all this hot water going towards the poles, and by conservation of mass, there's got to be then some kind of return flow going on. So you think, well, it's colder at the poles while we still have ice, so therefore you expect that to be water, deep water formation, which there still is, deep water formation that goes deep and has a return flow. Now, then you think, okay, but if that phenomenon is happening, I will have, what is stopping me just having a pool of hot water near the top that's going across, and then I have cold water underneath. Whereas it is observed that there is a pretty continuous stratification in the world's oceans. So that means there has to be something that is smoothing out, is transporting the heat downward from the top, or alternatively lifting coolth up from the bottom to make this continuous profile. And that means there has to be some mixing in the interior of the ocean that is doing this, that is smoothing out this stratification. And so that is the fundamental question. Can we understand that? Can we understand aspects of that mixing process to actually be able to model how we end up with the stratification that we have in the ocean, which is key to this overturning circulation, so we don't have, like, the day after tomorrow switch off of this Atlantic meridional overturning circulation, this AMOC that we kind of rely on. Okay, so then the question is, as I always do, I kind of look back at have looked back at old literature and thought about this. Now, this, in an engineering sense, is this fundamental question. You want to model this vertical diffusivity of heat, and throughout this talk, I'm not going to. The stratification in the ocean is dominated by temperature differences, not by salt, but in most of the world's oceans. So I'm going to be talking about the simplest case of stratification just with temperature differences. And so temperature and density I'm going to use interchangeably. And so really the question is, in an engineering sense, is how can you work out this eddy diffusivity for heat? So if on average I lift dense parcels up, I will typically be transporting, as I said, kind of this Coulf from the bottom. So that's the thing I want to know. But that is very difficult to work out average quantities of these second order correlations of fluctuation quantities, the vertical velocity and the density fluctuation. It'd be much easier in a classic sort of flux gradient way to be able to describe this in terms of the mean gradients that I can identify, the mean gradient to the density. And you'll notice the way I've written it here, I'm multiplying by G over some reference density. So the denominator there you see is actually a frequency squared. It has dimensions of times the -2. And that is because this is what's known as the buoyancy frequency, because if you think about it, if I lift a dense parcel up, it will feel a restoring force because it will be dense compared to its environment and want to fall back down. And so as it falls back down, it will have exchanged potential energy to kinetic energy, and when it's at its equilibrium level, it'll still want to keep going, so it will oscillate like a kid on a swing. And that oscillation means that the ocean is full of internal waves, because these waves exploit this oscillation for frequencies less than this buoyancy frequency of a vertically bobbing column. Then you can have waves bouncing around. And also there's a technical point, which is that it is very easy, not cheap, but very easy to measure vertical gradients of density. You can drop probes that measure the conductivity, the temperature, and the depth, and so then you can work out a mean profile of the density. So a holy grail is really to be able to describe the quantity you want, this on average lifting up dense parcels, in terms of this background gradient. And here's this picture of Walter Monk standing in front of the Scripps Pier down in San Diego. He really was an amazing oceanographer. There's a movie out at the moment about called Pressure, which is about worrying about the weather at the D-Day landings. But he was the person who worried about the wave state on the D-Day landings, whether it was possible for the amphibious things to land. And he wrote any number of crucially important papers. And one of the papers that he wrote was saying, if you think about the overall stratification that you see in the ocean, the ballpark figure you need to have for this eddy diffusivity compared to the molecular diffusivity of heat is something of the order of 1,000, right? So there's got to be quite a bit of such mixing going on in the world's oceans. And now, the modern thing to say is, okay, well, how would we model this kind of mixing? And the modern way to do it, of course, will be to ask the following question. What would AI do? But that isn't the question that I am trained to ask. I'm old enough. I'm not as Steve's young and thrusting. I'm older. I was trained in Cambridge, and the question that I was always told to ask was the following: what would GI do? What would GI Taylor do? And indeed, this was really the first problem that he considered. His first job, his permanent job, was as a reader of meteorology, and he went off on a survey, a government-sponsored survey of the North Atlantic that was sponsored to basically on the ship called the Scotia. And what it was actually why it was going there was to see why the icebergs were where the Titanic were there. That was a real surprise that there would be icebergs there. So they were trying to find out what the hell was going on to have the icebergs where the Titanic was. And during that survey, he did some really important measurements concerning stratified turbulence, which I'll talk some aspects about. But I brought up, I've made this silly little joke, but it also connects very much with Walter Monk, because in an interview with him, with his one of his former students, there was this question was asked. You told me that you have three heroes, Sverdrup, and I've mentioned this 100 million cubic meters of water per second, and that unit, the million cubic meters per second, is a unit called the Sverdrup, very, very important oceanographer who was actually his PhD supervisor. Ravel, who of course was the great organizer that really got UCSD built, where I was fortunate enough to work for a while, and G.I. Taylor. And so, yes, the three of them have been my role models, my teacher Sverdrup, my mentor Ravel, but if you have to use the word genius, Taylor is the one. I can imagine writing some of the papers Sverdrup wrote or fighting some of Ravel's battles, but G.I. never, right? And so why am I highlighting G.I. Taylor? Well, I'm highlighting G.I. Taylor because of the approach that he argued about how to solve this particular problem. I also like to highlight G.I. Taylor because the exceptional research group that he had in the 50s back in Cambridge with this particular amazing group of people. Along the front row, there's Tom Ellison. There's then Alan Townsend, who was really deeply important for turbulent shear flows. Of course, there's Taylor, there's Batchelor, there's then Fritz Ertl, who for a long time was great in ship hydrodynamics and was a professor in Manchester for many years. And then on the far right, Milton van Dijk, who was effectively a postdoc at the time there, and then went off to Stanford to be their first professor of aero there. There's Owen Phillips in the middle row, who was at Johns Hopkins for a long time and also did key contributions on this stratified turbulence. And Philip Safman, the other FRS in the back, who was at Caltech for many years. The connection between West Coast fluid mechanics and Cambridge runs quite deep. But on the far at the top right is Stuart Turner, who literally wrote the book on buoyancy effects in fluids and was my academic grandfather. He was the supervisor of my supervisor. But I show this picture because I want to say particularly about GI's philosophy about how to address turbulence, how to address this problem. Because in 1915, he wrote this essay on which has got a prize called the Adams Prize on turbulent motion in fluids, and that was recording many of the things that he did during the Scotia survey. Very interesting setup for that. It was supposedly anonymous. Of course, the people who are reading it would be able to know it was damn well it was G.I. Taylor who wrote it. But you had this handwritten cover to your essay, and that you had to then put a motto on it, which he chose that would then identify who was it when they decided who'd won the prize. And the motto he wrote was a quotation from Robert Louis Stevenson: "I saw you toss the kites on high and blow the birds about the sky," which is a beautiful concept of that description of turbulence. He did win the prize. The prize was worth enough to buy a house in Cambridge. The prize is still a given now, but it isn't enough to buy a house in Cambridge. That's a thing that I think Seattle people can understand that can happen. But he wrote a kind of a philosophical introduction to this essay, which I think is amazing. This is about turbulence. And it really speaks down the years to people who are now interested in data-driven methods. So at first sight, this, turbulence, appears to be so difficult a problem that a solution seems almost impossible. And so I believe it would be if one were to adhere strictly to the equations of motion without any other assumptions, which was fighting talk. When I give this talk in the maths department, it's fighting talks, right? But I've got engineers here, so that's okay. So the method, however, which I adopt in dealing with complicated problems of this kind is to guess at some result which I think would probably come out as an intermediate step in the complete solution of the problem. So to have a theory. Using this assumption, I then work up to the stage at which I can compare the results of my calculations with observations. Data is essential to this whole process. And if the observations fit in with the calculations, I then go back to the assumption and try to deduce it from the equations of motion. And so it really speaks down the years that, 110 years ago, he was saying how important it was to actually properly assimilate data into your modeling exercises, which is what I will be talking about, hopefully over the next half an hour or so. Right. So what's the fundamental problem, right? So I've mentioned we want to understand this eddy diffusivity, right? And so if you think about the energetics of the system, you see it's inherently related to energetics. So suppose we have some linear gradient in density, and we have we have turbulence, those little red eddies. Well, so what's the turbulence going to do? Is it going to do nothing to the background stratification, and you just retain the dash line? Is it going to really completely mix up that middle layer, and so we have the solid blue line, a uniform layer in the middle? Or is it going to be something in between, like the green line? But if you think about what's going on there, the blue line and the green line clearly have higher potential energy than the original case. So on average, you have indeed lifted dense parcels up. And that is quantified by this buoyancy flux, which is really a density flux, as one of the two sinks of the energy. You might have a turbulent production from shear or whatever, and then you have the classic viscous dissipation term, which is enhanced by turbulence. But you also have this buoyancy flux B. And so it's how are those two partitioned? That's really a question of interest. But I've talked about it in terms of energetics, but one of the problems with this, and there's been beautiful work done here by Eric DeSaro on this point, and Jim in the audience, but and Craig Winters, that was such a deeply influential paper. But the energetics, you'll see that when we work out this quantity, this W prime rho primed, you have a problem. I've said I'll lift dense parcels up, but there's no reason that I don't then put the dense parcels back down again. There could be a reversible component to that. But you can also think the kinetic energy is the second order correlation of fluctuations in the velocity. You can also think of the autocorrelation for density fluctuations. And when it's appropriately scaled, so it has the same dimensions as this kinetic energy density, you can recognize this is like a scaled buoyancy variance, if we say relative to some zero otherwise, right? And interestingly, I can write down a conservation equation in a very similar structure. The time rate of change of that is going to be balanced by some negative divergence of a flux, a transport type term. There's going to be this B that is negative in the kinetic energy equation is then positive here. So if on average I'm lifting dense parcels up, I will actually be increasing the buoyancy variance. But then I have a destruction term, a clearly identifiable destruction term, which is sign definite, that destroys the fluctuations. And just like the viscous dissipation term, it involves the diffusivity and it is sign definite. And so it is really not that you can really think that rather than trying to solve the problem with the eddy diffusivity, if I look at this chi, this destruction rate of buoyancy variance, it relative to the buoyancy frequency, then I can work things out. Now, also interestingly, if you can actually relate it to the kinetic energy model, that if this deviation is taken from a uniform constant gradient of density, like that blue line, then you can show a one-to-one correspondence, at least within this simplified model, between destruction of buoyancy variance and destruction of available potential energy, the potential energy that is actually available in the flow to drive fluid motions. So we want to work this out, and so then you naturally start thinking about, okay, what is the how we parameterize it? We might want to think about a way to describe it in terms of the viscous dissipation, try and identify this taxation rate, this rate that the partitioning of the energy that's lost from the mean flow. Some of it goes into increasing potential energy, some goes into increasing kinetic energy. Goes into viscous dissipation, right? Problem is, you can't do anything with this, right? I wrote a review article 5 years ago and basically politely said nobody knows what's going on, right? So it still remains extremely difficult to say anything generic about mixing. There's a real problem with having a generic argument. A very influential paper, however, said that, okay, it seems that this taxation rate, this ratio between the amount of the energy that's going into increasing the potential energy as opposed to the amount that's going into the internal energy via viscous dissipation, seems to be bounded above by about 0.2. And so that then seems to be a nice way to look at this problem, because then the thing I want to know, this eddy diffusivity, I can express in terms of the viscosity, which I hope I know quite well, this constant taxation rate, and this intensity of the turbulence, this buoyancy Reynolds number. And embedded with that, within that, is a kind of it's an issue with language. It's not it's kind of saying that the mixing is relatively weak. Obviously, it's relatively weak because only 20% of the energy goes into the buoyancy flux as opposed to into the viscous dissipation. But it is kind of saying that the turbulent Prandtl number, the ratio of the eddy diffusivity of the momentum compared to the eddy diffusivity of the heat, is about order 1, which means that the stratification isn't much modifying the turbulence. Of course, the stratification definitely is affecting the turbulence because it's extracting some of the energy, but it's not really damping it down. It's not really killing it. And this comes through just in this really quite simple combination of manipulations. This is the definition for the eddy diffusivity of the density. If I multiply that above and below by G over the reference density, I get this buoyancy flux over n squared. And as I said, that could be related to this destruction rate of the buoyancy variance compared to the buoyancy frequency squared. If I think of the eddy diffusivity for momentum, this is just its definition. If I multiply above and below by du dz squared, I get this expression. And so therefore, the turbulence production is on the top, and I have the square of the shear rate on the bottom. And so the turbulent Prandtl number, the ratio of the two, is just the buoyancy flux underneath the production, which is when it's in balance, the production is the same as the eddy diffusivity, as the same as the viscous dissipation plus the buoyancy flux. And this ratio of timescales, which is called the gradient Richardson number. And so the turbulent Prandtl number is just the ratio of the gradient Richardson number to this efficiency, this flux Richardson number, which can be written in this particular way. And so if the turbulence is relatively weak, we expect that means that this will be about 1, which would mean that the flux Richardson number and the Richardson number should be about the same. So that's a kind of testable hypothesis. Now, unfortunately, it's not clear that can we see that? And also we have other questions about how can we actually understand the mechanics by which this kind of mixing might take place. So let's actually now think about the real, follow G.I. Taylor's philosophy and actually look at the real ocean. And so think about the various values that the possible parameters have in the real ocean, right? So apparently, if you actually do, this is another deeply influential paper nearly 20 years ago now, about thinking about what the Reynolds number and this quantity, Froude number, which you should think of as the square of the Froude. This Froude number is like the inverse of the Richardson number. So small values of the Froude number correspond to very strong stratifications. And if you think about what's the situation in the ocean is in a very interesting distinguished limit. It typically has very, very large Reynolds numbers associated, where if you define the Reynolds number associated with the horizontal velocity and the horizontal length scale, that's very, very large. And yet it's very strongly stratified in the sense that the time scale for one of these very large eddies to turn around with this horizontal velocity and horizontal length scale is very slow compared to the time scale of the buoyancy frequency wanting to push things down. So the horizontal Froude number is also very small. So that's what's shown here. This 1 over it is about 10 to the 3 is the estimate for the ocean. Now, but it's also thought to be in a particular distinguished limit, which is associated somewhat with the saying that if you think the natural scaling, which actually once again is a Taylor natural scaling, for the dissipation rate, you would expect for such a patch of turbulence that the scaling for the dissipation rate to go like U cubed over L in terms of these horizontal scales. If you then make that assumption, you'll see that the equivalence requirement, if you want the buoyancy Reynolds number, this intensity of the turbulence, epsilon over nu n squared, to be very large, that requires the Reynolds number multiplied by the Froude number squared. You'll see that that gives you the epsilon naturally, because the Reynolds number has a 1u on the top, and the Froude number has a u on the top, so I need to take Reynolds by Froude squared to get the u cubed on the top. I need that distinguished limit to still be large. Now, why do I want the buoyancy Reynolds number to be quite large? Well, that then tells me these are all interconnected concepts, but that is because we want a separation of length scales. Now, we know from turbulence, the smallest scale that kills everything kills all the velocity fluctuations is the Kolmogorov scale, given in terms of is nu cubed divided by epsilon to the quarter. So it's 1 over it in that square bracket. But the buoyancy Reynolds number can be written as, to the 4/3 power, the Kolmogorov scale on the bottom and this Osmodov scale on the top. Now, the Osmodov scale is a scale constructed from the dissipation rate and this buoyancy frequency. And since the dissipation rate goes like L to T minus 3 and the buoyancy frequency goes like T minus 1, that epsilon over n cubed to the half is a length scale. And once again, we can think about this length scale in terms of energetics. If we have an eddy overturning, it continually will be exchanging kinetic energy into potential energy. And so you might think, okay, well, as I make the eddy bigger, doing that overturning is going to cost me more potential energy. The Osmodov scale can be thought of as the scale of an eddy which has just enough kinetic energy to be able to convert itself to potential energy and goes up to the top. Just like being able, a game I played when I was a kid with, maybe I haven't always thought about this, but when you have a bucket, right, you have to, when you spin a bucket, you have to spin it fast enough to keep the water up. It's not unrelated to that concept. It's that, do you have enough energy to be able to go over the top? And if the eddy is bigger than that scale, well, you'll think, okay, you would really expect the stratification to strongly affect you. So the Osmodov scale is the largest scale that you've got a chance that the stratification isn't strongly affecting the overturning. And so a large value of buoyancy Reynolds number is now saying that there's a large enough dynamic range between the scales that start to be strongly affected by stratification and the scales that that are really being killed by viscosity. So the only chance you have for any sort of classic isotropic cascade is for those scales to be quite widely separated. And indeed, that's the regime that we're thought to be. Now, then you just say, okay, you've constructed scales that involve the turbulence. What about constructing a scale that knows about the large-scale properties of the flow, the velocity UH and the buoyancy frequency N? And you can define that that's a buoyancy scale that just naturally emerges, and it's distinct from LO. It doesn't necessarily know, it's not directly related to knowing anything about the dissipation rate. Now, the great thing in this paper, and the sequence of papers by these 4 people, really says that there's a plausible ordered set of scales that you could imagine, where this horizontal scale of this patch of turbulence is very much larger than the vertical scale, so it looks like a pancake. So the horizontal scale is this scale, and the LV is this yellow scale. But then that scale is still very much larger than the Osmodov scale. So for scales between here and here, we expect the vertical motions to be strongly affected by the stratification. So we expect anisotropy. We expect vertical motions to be very much smaller than horizontal motions. But then, because we want to have this dynamic range, we want this Osmodov scale to still be a hell of a lot bigger than the Kolmogorov scale. And so we want to have with the possibility of isotropic turbulence below those scales. Now, this has 2 really interesting implications, testable implications. This was an old simulation, but it kind of shows this layering emerging and this anisotropy. First one is that if you have this big patch that's got some characteristic velocity, horizontal velocity, and some characteristic vertical scale and length scale, and it meets another patch, it's entirely conceivable that in a region like this, the local vertical shear can be enormous, and no matter how strongly stratified you were, you'd expect your Richardson number to be small, and if your Richardson number were small, you might be able to have shear-driven overturnings. So you have built-in possibility of intermittent, vigorous turbulence. But also, and I certainly don't have time to talk about this, there is an argument that even for scales larger than the Osmodov scale, you expect the possibility of the energy spectrum for the horizontal wave numbers to go like k to the minus 5/3. This is not saying it's Kolmogorov-like turbulence with isotropic k to the minus 5/3 for the isotropic wave number. It's a statement about the horizontal wave number. Now, this is the guess bit, right? Does this actually exist? And so you want to see if there are observations. Now, fortunately, or unfortunately, I keep using that is confusing to have two and only one. Well, it confuses me. So, does this exist? Now, fortunately, around these islands that you may, depending on your political background, they're either the Malvinas or the Falkland Islands. There is known to be a vast amount of hydrocarbon reserves. I'm sure that had nothing to do with Margaret Thatcher's defence of democracy. And because there's a large amount of hydrocarbon reserves, there have been surveys, seismic surveys of which are extremely expensive to generate. What you do is you have a boat with air cannon that sets off very large bubbles to induce sound waves in the water, and also that will then propagate into the subsurface. And they, of course, in a classic reflection transmission situation, if the medium changes, some of the signal will be reflected back, some will be transmitted, there'll be some modification. So if you have a long streamer of hydrophones, 5 kilometers long, 240 receiver groups, taking these measurements costs in the tens of millions of dollars, you are able to get a clear picture of the subsurface. And if you can then deduce from that how much oil is, the potential for there to be oil and gas down there. But a colleague of mine, and indeed a guy called Holbrook was the first person to appreciate this, a colleague of mine called Nicky White, who is a subsurface seismologist, realized that also, similarly, as you went through the water column, changes in the properties of the water column will also lead to seismic reflection. And so you're able to infer differences in the water column structure from these signals. Now, if you then are in good relations with an oil company, you can say, okay, we don't care about the subsurface. You don't have to give us that data. Just give us the ocean data. So here's the ocean data, roughly contemporaneous, 80 kilometers in that direction, a kilometer in this direction. And if you zoom up, if you then look, so you see these structures, but remember that since this is 80 kilometers and that's 1 kilometer, all these wiggles are very, very close to being horizontal. And so you look at places where there's a big change, and that's associated with temperature and hence salinity and hence density variations. You see that there are jagged lines, and you take that picture and you zoom it up, and you go over here and you see, oh, there's still jagged lines. So I zoom it up, and so now I'm in a situation where this is 150 meters, and that's 10 kilometers. And I then take the picture again and zoom it up, and I can still see jagged lines in the data, even down to something of resolution of 20 meters in this direction, 2 kilometers in that direction. So I'm seeing very, very close to the horizontal wave number of fluctuations. And so therefore we can spectrally analyze this and see if there's this signal. And this is the data. What we've done here is we've taken the energy spectrum and multiplied it by k squared. It's called the slope spectrum. It's like we're looking at the entropy spectrum rather than the velocity spectrum. And to aid your eye, we've got a slope here of -1, and we've got a slope here of 1/3. So the -1 is very close to EK being k to the -3, which is waves. And then down to a scale when this normalized wave number corresponds to about 300 meters. There's no way, the Osmodov scale here is, 1 meter, 2 meters. There's no way that this is isotropic turbulence. We see k to the 1/3. Very, very clear signal. So there's definitely is this strongly stratified turbulence regime actually exists. Now, the question is, and I've talked about the Richardson number issue. The question is, you know, when you have a low Richardson number, you can have an instability, but this is associated with flows that seem to be very far from very strongly stratified in this particular regime. So the question is, how can we have turbulence with or without instability? Now, you go back to the old literature and you look at the absolute original paper, the Reynolds 1883 paper, and showed this amazing intermittency, these famous experiments. But what is perhaps not as well known is the original referees report written by George Gabriel Stokes on this particular paper. And there's two lines I want to highlight. This one, I consider Professor Reynolds' paper a valuable one, which I recommend should be printed. He shows for the first time that a distinction between regular and eddying motion depends on a relation between the dimensions of space and velocity, or what comes to the same as space and time involved in the experiments. A fact pointed out by the known equations of motion. He shows also that, this is the key sentence, one of the key sentences. He shows also that the one class of motion passes into the other with an unexpected suddenness. So in our jargon, that means there doesn't have to be a linear instability, which indeed we now know there definitely isn't to be triggering this is non-normal. But this other bit is quite entertaining, particularly for the younger members of the audience. In one part, the language seems to imply, and he then inputs, which was not perhaps his intention, that he had discovered new dimensional properties of fluids and might even lead to the supposition that he supposed that he had shown that another constant beyond those recognized was necessary in order to define a fluid mechanically. This certainly is not the case. The dimensional properties are already obviously involved in the equations of motion, and there is absolutely nothing to prove that he has discovered the necessity of an additional constant to define a fluid. We now call that constant the Reynolds number. So, if you have somebody gives you JIP in a referee's report, don't necessarily rebut it confidently, right? So then let's see further observations. Can we see these sorts of properties? So this is a wonderful set of observations taken by the UCSD group of Jen McKinnon and Matthew Alford off Palau, which is an island in the South Pacific. One of my greatest regrets was saying I was too busy to go on this particular cruise. So they took direct measurements of the key quantities, epsilon, chi, and n squared, direct measurements of this reef along this line. And here is the signal. You know, this is over hundreds of meters in depth, and you'll see that this dissipation rate, epsilon, and this mixing rate, chi, can vary by orders of magnitude. This is a logarithm, right? And it's varying between -10 and -6 in SI units. And so the question was, they took about 300 profiles, and what we said was, well, and then they published a paper that was a traditional way of analyzing this. And our idea was, well, what would happen if we did some unsupervised learning on this data set and actually looked to see what parts of the flow mattered or not? And so the idea was, okay, we would take all these profiles and we'd construct 3D points in phase space where we had a value of epsilon and a value of chi and a value of n squared from about 30 meters by taking rolling windows of the data that we had. We had epsilon, we had chi, we had n squared. And so we would construct these points in 3D space, which had a given value of epsilon, a given value of chi, and a given value of n squared. And so we ended up with 40,000 of them when we did this. And then what we decided what we was going to do was going to say, can we identify clusters of characteristic behavior? And the way we did that was by using this really simple, but it worked really well, algorithm called optics. And so what you want to do is you want to identify classes of events, which are mixing epsilon, chi, and the associated n squared, that have things in common. So there's lots of points relatively close together that have the same kind of properties. And so what you do is you define this reachability for every point. And remember, this is a point in 3D space, right? The x coordinate is epsilon, the y coordinate's chi, the buoyancy frequency, the z coordinate's n squared. And you say, okay, I've got 2 points. There's some simple Euclidean distance apart. But also, I want to know if each of these points have got a lot of neighbors. So we say that we define another length scale, the radius of a sphere in this parameter space, that includes a certain number of points, a certain number minimum points, which we set to 1,000. So you'll see, and then you do this for every single one of your data, 40,000, and then you just line them up one after another, and you see if you can identify valleys in the data. Values with relatively low this reachability distance, the minimum of the distance apart and the radii of these spheres around it. So here you see these red points here are really, there's lots of them and they're tightly clumped, so their reachability distance is small, whereas there's a group that's identifiable as, which is within a valley, but it's kind of up in the mountains because it's quite spread up and it's quite spread out. And so you can see, you can get a certain amount of points that emerge. And the thing that happened for us, which was surprise, was that we identified 5 valleys in the data. That's actually the real data that were separatable into 2 broad classes. There were the cold colors that were associated with weak stratification, the blue and the purple one. And then there were higher stratification ones, the yellow, the red, and the orange. And if we then represent them in 2D space, you'll see that the colder colors have epsilon, but they have very little mixing. They're small values of mixing, whereas the hotter colors are ordered in the amount of mixing. There's an interesting subtlety note, though I said they're strongly stratified. The one with the most mixing is actually the one, not the most strongly stratified, but the second to most strongly stratified. Here we have, oh no, no, sorry, I'm saying exactly the wrong thing. It is associated with the strongest stratification. You'll see that this is the dissipation rate. You see these guys have 2 different levels of dissipation, but they are definitely in weakly stratified regions, whereas these guys are very high dissipation rate, and they're associated with strong stratifications. And then this is the n squared against the chi. Once again, these are ordered by their mixing, and this group does very little mixing and is because it's in weak stratification. So this has emerged from looking at the data agnostically, rather than applying any model to what was going on, but saying that we might be expecting to have strong turbulence. And then but I haven't told you other information. These are measurements from profiles, so we can now start to interpret it by where they were located. So this is a plot of the distance offshore, and then the distance and the depth. And you'll see that you can now really interpret what's going on. The blue, remember this was highly turbulent, but weakly, but not doing much mixing, is stuff near the surface, right? It's at high levels, which is weakly stratified up there, and that's like wind-driven turbulence. The purple is stuff that's near much deeper down, where it's weakly stratified again, not much mixing. It's not so strongly turbulent, but it's like bottom roughness is driving it. But the thing that was surprising to the oceanographers is that the strong mixing events are all associated with the region where the density gradient is high. And we're not associated with overturnings. The classic idea is that it's associated with these sort of Kelvin-Helmholtz overturnings you see in this experiment up here. Tilting tank, fresh water runs up, salty water comes down, and you have these overturnings. But that didn't seem to be the case. When we looked at the overturnings, because we could also see from the density profiles whether there was overturnings, a measure called the Thorpe scale, there was no Thorpe-like mix, no overturning measurable, which was a resolution down to 50 centimeters when we were strongly turbulent. That's something I'm going to come back to. It's not that the resolution said there wasn't an overturning, or that the overturning had to be smaller than 50 centimeters, which is something we can now test further. Okay, in light of the time, I'm going to skip the next one. We could tell about where it was about different currents. But we also found a key, another really important aspect of this data was that the total amount of mixing was dominated by extreme events. So we looked at the total amount of mixing that was going on in the flow, and we ordered it by how much mixing, the total contribution to chi, from the smallest to the largest value, the highest value, and then the cumulative amount that it was making the contribution. And the thing I want to draw your attention to are the red lines, which are the most vigorous ones. You'll see that 15% of the points are doing 90% of the mixing, and yet they are only doing about 65% of the viscous dissipation. So it's saying that most of the mixing is associated with very rare events that aren't associated with overturning, so it could be strongly stratified, and they are situations where the viscous dissipation isn't quite as large, right? The constant taxation rate isn't working. It's effectively saying that the situation is like Europe. Most of the taxes are being paid by the really rich people at a higher taxation rate than the average. And so the thing you need to think about are the rare events. And so this isn't saying that Osborne was wrong. If you then plot again the value of this ratio, this taxation rate, against how much mixing is going on, and you'll notice this flux is varying by 6 orders of magnitude in this plot. You'll see that 80% of the points are really clustered around the 0.2 value for the mixing. So most people are paying 20% taxes. But the stuff that matters is in this very, very efficient, very rare events. And remember, they seem to be associated with more strong stratification. So this is direct observation, but of course we can measure what we can measure. It's a tour de force to be able to measure epsilon, chi, and n squared. Let's try and understand it by doing a numerical simulation. Problem is, you have to do very big numerical simulations to capture any aspects of these flow properties, right? Particularly because the Prandtl number is important. Now, the Prandtl number is in the ocean is of order 10. You know, that's the ratio between the viscous dissipation and the viscosity and thermal diffusivity. And high values of that means that you can have very fine scales in your temperature field, even when you are being viscously dominated. And so, but if you want to retain the resolution of those fine scales, you need to go to quite a large resolution, which is what Nico did with Steve de Bruynckops, these very high resolution simulations. So we forced them with low wavelength injection of energy, low wave number, large wavelength, horizontal energy. And we kept forcing them so that they had a buoyancy Reynolds number of about 50. That's not really very extended, but it's what we were able to do. And we did 2 different classes of simulations. We did them Prandtl number 1 and Prandtl number 7 as a model of the ocean. And we did a situation where it was weakly stratified and then strongly stratified. And so you see, I'll try and represent the figures like this. High Prandtl number, real ocean on the lower row, and weakly stratified on the left column, strongly stratified on the right column. Now, what I'm plotting here is the ratio of the fluctuation vertical gradient compared to the mean gradient. And so blue lines correspond to strongly stable regions, and red corresponds to statically unstable. And this is the one that's the most important always. This is the strongly stratified high Prandtl number case. And you'll see the screen is screwing us up a bit, but you get an impression that it's quite pink. So there's a lot of relatively weak, statically unstable regions, which is crucially important. So this is a horizontal slice of the dissipation. You'll see when we are weakly stratified, we nucleate into vertical vortices, basically. But then when you make it more strongly stratified, you start to see these kind of patches, these kind of pancakes that we wanted to have. So what? Well, we have loads and loads of data. There's, over 3 billion data per snapshot. It's quite a lot. So Nico's idea was, well, let's segment the data into 4 different groups. So you can see these strongly stratified interfaces, they emerge, these dark blue lines. And they certainly are there. But then there's also regions that are strongly statically unstable. He marks as dark red. And what he defines as strongly stratified unstable, looping back to old G.I. Taylor again, is the scales where viscosity starts to affect the cascade. They're called the Taylor microscale. So he then plotted in this sort of orangey color over statically unstable regions which were extended over a distance below the Taylor scale. So that is saying they are being affected by the viscosity, small overturnings, but they still are statically unstable, and there's still a lot of fine structure because you have higher Prandtl number. So that's the situation he did. So if we do the Prandtl number 1, we see, well, there's a lot of these Taylor scales, but we also see a lot of these strong interfaces, these sharp interfaces. You see a lot of blue. You don't see, consistent with the oceanographic information, you don't see big overturnings much. You really can't see any red at all. There's really not much big overturnings going on. But when you go to Prandtl number 7, the significance of the sharp interfaces disappears, and you really get this overwhelming impression, particularly in the strongly stratified case, that it's all orange, which means their small-scale overturnings is really what matters. But if you then do the same thing about ordering your data, we see a very, very consistent argument compared to what we saw in the real oceanographic. So once again, here what we're doing is we're saying the fraction of points, these are the most important ones doing most mixing. These are the ones doing the least amount of mixing. This is weakly stratified. This is strongly stratified. This is Prandtl 7. That's Prandtl 1. And this is the cumulative amount of the total amount of mixing by the number of points. Strongly stratified Prandtl 7, you'll see that 90% of the mixing is being done by 20% of the points. And they are virtually all in this lamella region, i.e. below the Taylor scale, but weakly stratified. So once again, these various dashed lines correspond to the value of chi, and gamma, and you'll see once again, for these guys that are doing most of the mixing, they're extremely efficient. They have very large values of gamma. So we seem to see that what really matters for this mixing is extreme events that are associated actually with small-scale overturnings that are just right for making everything happen. And so then the question to do, because this was point by point, is how to connect this with the real world, where you have to do actually some averaging of the domain. And that is a great challenge, which also is something, just as I come to the conclusions, that you see averaging has still not been fully resolved. Because here's the other great paper that Reynolds wrote about Reynolds averaging and the Reynolds stress. This was the paper that he wrote in 1895, 94, 95. And this is Stokes' review of this particular paper, which also speaks down the years. This was written to Lord Rayleigh. I must plead guilty to not having digested Professor Osborne Reynolds' paper, though much time has passed since it was referred to me. I find it very difficult to make out what the author's notions are. As far as I can conjecture his meaning, I must say I do not think he has made out his point. He is, however, an able man, and in his former paper, i.e. the one I just mentioned, did very good work in showing that the conditions of dynamical similarity which follow from the dimensions of the hydrodynamical equations, when viscosity is taken into account, are not confined to what I may call regular motions, but continue to apply in relation to mean effects even when the motion is of that irregular kind which constitutes eddies and which at first sight appears to defy mathematical treatment. So it seems like Stokes had at least understood the previous paper by now. So, but this is the real thing, particularly in my role as editor at JFM. The fact that the author has gone to the expense of printing the paper shows that he himself considers it of much importance. Pay to play. It's still, it was the same 100 years ago. I confess I'm not prepared to endorse that opinion myself, but neither can I say that it may not be true. I do not know whether these remarks will be of any use in assisting the council to come to a decision, but they still publish the paper and we still talk about Reynolds averaging, so it's all okay. But once again, do not be discouraged by senior people not really reading your papers when it's being reviewed. Okay, so here are the conclusions. It seems that this regime is in the ocean. The simulation is extremely challenging, but extreme events seem to be very important. And there is an enormous range of scales that go on. And so actually, fundamentally, going back to Taylor's philosophy, I think there's been a real problem with people trying to test starting from a theory and looking for the theory, like looking for overturnings, looking for Kelvin-Helmholtz, saying the mixing that matters is associated with the overturnings. That we really must change and develop algorithms to look at data, to sniff around in data, I guess it's now, we call it agents, to actually try and see what are important structures that we then might want to think about. And really, that seems to be the case. By effectively reanalyzing observational data, we came to a completely different set of conclusions from the original study. But neither were wrong. It was just they analyzed it in a different way from the way we did, and we found new ways to interpret the data. So with that, thank you very much for your attention.
Online as well.
Yes, Jim. Yeah. Oh, so in the observations, the observational data, they did also measure the shear, but at somewhat lower resolution. And they were in the ones in the thermocline related ones were higher values of chi were associated with higher values of shear, but still they were not measurably associated with overturnings. And I'm very wary to kind of quote Richardson numbers associated with the individual measurements, because it really is a thing that their resolution of the shear was so large that it would seem that the Richardson number was big, but it didn't mean that locally, they didn't have enough resolution, and there could have been a local patch that it was. Once again, a important point is that they were measuring the vertical shear, and I think the thing they're really missing is horizontal shear, is actually horizontal shear in these particular places, because that seems to be a very, very efficient way to inject energy. And I think that was clearly the case in the Petropolis simulations. That you had an overturning that was relatively small in this scale, but still you had really intense velocity in shear in both directions. Contributions of du dy or dv dy or dv dx was also very significant, as opposed to a du dz. Everybody wants their lunch. Crikey.
It's basically saying, like, if you can foresee that any of the policy changes that have been around the world.
Well, so there's I think a enormously valuable aspect for the ocean is still very poorly measured compared to the atmosphere, and the more that it is measured, the more that we find new things to look at, and new processes that may matter. I think there are two issues: is both the issue of supporting observational studies that are transnational, and then also saving the data, keeping the data available and on repositories. It has unfortunately become a bit politicized, because the observation, what I'm talking about here is understanding the ocean, and I presented it through the framework of understanding it for getting adequate information about how the climate changes. I can tell you two really strong commercial reasons independently, or two really strong reasons that are not usually associated with understanding the climate, the understanding the properties of the ocean, that are critical. The first is the primary mechanism by which hurricanes are intensified is to do with heat transfer between the surface of the ocean and the atmosphere. understanding how much fuel there is, how deep it is, and where, and so on, is a critical question that is literally worth trillions of dollars in the global insurance market. And so, for example, we are going to have a stronger El Nino. How will that, which is just empirically observed, how will that affect the risk of a big hurricane hitting New York is a thing. The second thing is various communications and monitoring purposes. There are many geopolitical reasons why people are very interested in being able to detect the motion of objects in the ocean. How sound propagates in the ocean is a strong function of the stratification and the forms of the stratification and interacts with the turbulence. So you really need to know how that interacts to be able to understand how solid objects move around in the subsurface. And that is deeply important geopolitically, irrespective of any changing of climate change discussions. So there is a hope that it will be retained. There is a concern, though, from what's happening with atmospheric measurements that they're being pulled back, and those are crucial to modelling the climate too, of course.